Our Earth is a rather special place, isn't it? It's not just a lump of rock spinning through space. Deep beneath our feet, something quite extraordinary is happening. This activity generates a vast invisible force field. We call this the Earth's magnetic field. It stretches far out into space like a giant cosmic bubble. Without it, life as we know it might not even exist. It acts like a shield, deflecting harmful solar winds and cosmic rays. Think of it as Earth's very own superhero cape, always on duty. Now you might wonder how this enormous magnetic field comes to be. The answer lies deep within our planet's core. The Earth has layers, much like an onion. At the very center is a solid inner core, mostly made of iron. Around this is a liquid outer core, also predominantly iron. This outer core is incredibly hot, thousands of degrees Celsius. And it's not static, it's churning and flowing like a vast, slow-motion metallic ocean. This movement of molten iron is the key to everything. This churning molten iron acts like a giant electrical generator. It's a process scientists call the geodynamo theory. As the Earth spins on its axis, the liquid iron in the outer core also moves. This movement of conductive material creates electrical currents. So this sloshing, superheated metal deep inside our planet is constantly creating the magnetic field that envelops us. Now, if Earth has this big magnetic field, you might think it would be easy to get electricity from it. After all, we know that moving a magnet near a wire can make electricity flow. This is a principle called electromagnetic induction. Michael Faraday figured this out way back in the 19th century. So the Earth is a giant magnet. Why aren't we all plugging our toasters directly into the ground? It sounds simple enough, doesn't it? Well, there's a rather significant snag. To generate electricity using induction, you need relative motion. The conductor, say a piece of wire, needs to move the magnetic field lines, or the magnetic field needs to move past the conductor. If the conductor and the magnetic field are moving together, perfectly synchronized, then nothing much happens. This, in essence, has been the big problem with trying to tap into Earth's magnetic field for power. Imagine you're holding a copper loop, hoping to generate some current. Enter the bright minds at Princeton University. They looked at this old problem with fresh eyes. They knew about the synchronized motion issue. They understood that simply laying out a wire wouldn't do the trick. So, they had to think differently, to devise a way to create a kind of local, artificial difference in how a conductor experienced the Earth's magnetic field. Their approach was not about grand, sweeping motions, but something far more subtle and contained. Their solution involved a hollow cylinder made of a common metal, like copper or brass. The idea was to create a situation where different parts of the metal experienced the Earth's magnetic field in a slightly non-uniform way. They weren't trying to stop the Earth from spinning or hold a piece of wire still in space. Instead, they aimed to create a localized effect within their device. The Princeton team realized that if they could make the magnetic field interact with their metal cylinder in a specific, controlled manner, they might be able to coax some electrons into moving. This approach was innovative because it sidestepped the macro problem of Earth-scale synchronization. So what did all this clever thinking and careful engineering achieve? Did lights flicker on? Did bells ring? Well, not quite on that scale. The Princeton team managed to generate an electrical potential. The amount they measured was 17 microvolts. Now, a microvolt is a very, very small unit of electrical potential. To put it in perspective, a single AA battery produces about 1.5 volts. So, 17 microvolts is undeniably a tiny amount of electricity. It's not going to power your kettle, let alone your house. But here's why this tiny number is actually a very big deal. Before this, reliably and demonstrably generating any electricity directly from the Earth's static magnetic field in this manner was exceptionally difficult. The 17 microvolts achieved by the Princeton team was a clear, measurable signal. It was proof that their concept worked. It showed that their hollow metal cylinder approach could indeed overcome the long-standing obstacle of synchronized motion and induce a current, however small. It was a spark, a tiny flicker, but a profoundly important one. The significance isn't in the quantity of power generated, not at this stage anyway. Alright, so 17 microvolts won't be powering cities anytime soon. We can all agree on that. But does that mean this breakthrough is just a scientific curiosity, destined for textbooks and not much else? Not necessarily. Even very small amounts of power can be incredibly useful, especially if they are continuous and freely available. Think about devices that need just a tiny sip of energy to operate. particularly in places where batteries are impractical or impossible to change. This is where Princeton's discovery might find its first real-world applications, powering the small and the remote. Consider, for instance, off-grid sensors. Scientists and engineers deploy vast networks of sensors in all sorts of inaccessible places. Changing batteries in thousands of such devices, scattered across difficult terrain or submerged in the ocean, is a logistical nightmare. A device that could trickle charge itself using Earth's magnetic field could operate autonomously for years, even decades. Then there's the realm of deep space exploration. Imagine if a spacecraft could supplement its power by harnessing the magnetic fields of planets it passes. So, what does this all mean for the future? Is this Princeton breakthrough the herald of a new age of Earth-powered everything? Probably not in the way we power our current energy-hungry world. We won't be replacing vast solar farms or wind turbines with giant metal cylinders just yet. The amount of energy, even if scaled up significantly, is unlikely to compete with these established renewable sources for large-scale power generation. However, that doesn't diminish the profound importance of this discovery. It's a significant step in understanding and interacting with our planet's natural forces. The real significance lies in the opening of a new frontier in energy harvesting. It's a proof of concept that could inspire a whole new field of research. Scientists will now be looking to understand the underlying physics even better. They'll be experimenting with different materials, different shapes, and different configurations to see if they can increase that 17 microvolt output. Could they get to millivolts? Perhaps even a whole volt from a compact device? These are the questions that will drive future research. Every new technology starts small, and this is no exception. The future of this research is unwritten, but it certainly looks a lot more interesting now.